Getting information from the graph of a function. The graph of a function can be very useful. For example, suppose the graph here represents the temperature in Fahrenheit at various times of the day. And in this case, it gives the temperature between noon and 6 p.m. So 0 represents noon and 6 represents 6 p.m. And you can see the various temperatures at particular times throughout that time period. So for example, if we want to find T of 1, which would be the temperature at 1 p.m., all we have to do is go to the graph on the x-axis here, which represents time. And when time equals 1, we can trace up to the function here, and we can see that the temperature is right around 25 degrees. So we can say from the graph that T of 1 is approximately equal to 25 degrees Fahrenheit. T of 3, same idea, at 3 o'clock. T of 3 is right here, which appears to be around 30 degrees Fahrenheit. And T of 5 appears to be around 20 degrees Fahrenheit. And notice that we didn't have to use any complicated equation or anything like that. All we have to do is understand how to interpret the graph. For the second part, they ask, which is larger, the temperature at 2 or the temperature at 4? So larger would be the one that is higher. So T of 2, we can see, is up here. That's somewhere around 34 degrees. And T of 4 looks to be around 25 degrees. So the answer to part B is T of 2 is larger. For the next part, it says, find the values of x for which T of x is equal to 25. In other words, at what time of the day is the temperature equal to 25? So if we go to our graph here, we can see that the temperature equals 25 right here. And if I trace this across, we can see the graph attains that value at 2 different times. And it appears to be at 1 and also at 4. So the values of x are going to be x equals 1 and x equals 4. And keep in mind, this means that the temperature is 25 degrees at 1 p.m. and also at 4 p.m. And next it says to find the values of x for which T of x is greater than or equal to 25. So again, here is 25 on the t-axis. We can see that the times where that is equal is at, again, 1 and 4. Now, where is the temperature greater than or equal to 25? Well, that would be here, right? Because greater than means the temperature is more than 25. Now, when does that happen? On the x-axis, this happens for all of the x values between 1 and 4. So I can simply say this happens when x is between 1 and 4. Or if I choose to write this in interval notation, I can write it like this. Or I can use words and I can say this happens between 1 p.m. and 4 p.m. And finally, find the net change in the temperature from 1 p.m. to 3 p.m. So what we're doing here is we're finding the net change from x equals 1 to x equals 3. And remember, the net change says you take the function value at the second x value minus the function value at the first x value. So T of 3 appears to be 30 degrees Fahrenheit, and T of 1 appears to be 25 degrees Fahrenheit. And so the net change is 30 minus 25, which is 5 degrees Fahrenheit. And what that means basically is between x equals 1 and x equals 3, the temperature changed from 25 to 30. So we have a net change of positive 5 degrees. Next, the graph of a function can make finding the domain and range very simple. Suppose we have a graph of some function y equals f of x, and let's suppose this is the entire function right here. The domain is the set of x values for that function, and so if we just map this down to the x-axis, you can see that the domain will be all of these x values, and the range is all of the corresponding y values. And so if we project this onto the y-axis, you can see that it's all of these y values here. So if you have the graph of a function, finding the domain and the range can be much simpler than if you don't have the graph. For example here, use a graphing calculator to draw a graph of f of x equals the square root of 4 minus x squared. Now I went ahead and did that, and what you see is that you get a semicircle. You get the top half of a circle of radius 2. And now it says to find the domain and the range of this graph. So again, if you just look at the graph itself, this graph covers all of the x values on the x-axis between x equals negative 2 and x equals positive 2. So I can say that the domain of this function is all values from negative 2 to 2, including. And then the range would be the set of all of the y values. And so we can see that the graph here covers all the y values starting at y equals 0 and going up to positive 2. So the range is all of these y values. And we can write that as the range is all values from y equals 0 to y equals 2. Graphs can also make solving equations and inequalities much simpler as well. Suppose that we would like to find the solution to a function f of x being equal to a function g of x. So graphically, if I have the graph of f of x here, and I have the graph of g of x here, what we're looking for is the x value for which the y values are the same. So basically, we're looking for the points of intersection. So we can see there is a point of intersection here, and there is a point of intersection here. And the values of x at those points of intersection would be the solution to the equation. So in this particular graph here, we would say f of x is equal to g of x when x equals a, and also when x equals b. And then we can also use it to solve inequalities. So if I say something like solve the inequality f of x is less than g of x, you just need to remember that f of x is a y value and g of x is a y value. So we're asking, when are the y values on the g of x graph larger than the y values on the f of x graph? So what that means is g of x needs to be above f of x. Or you can think of it as f of x must be below g of x. And you can see that that happens right here. F of x is below g of x right here. And that happens for all values of x between a and b. Now out here, of course, that's not a solution because this is the graph of f here, and this is the graph of g here. Likewise, this is the graph of f here and the graph of g here. So if we're looking for where f is below g, that only happens right here in this case. So for example, suppose we want to solve the equation graphically. In part A, we have 2x squared plus 3 is equal to 5x plus 6. So if I think of the function 2x squared plus 3 as the function f of x, if we graph that, we get a parabola. And then g of x, we'll think of that as the function 5x plus 6. That's just going to be a straight line. And you can see that this line intersects this parabola at this point here and at this point here. And it appears that the x value here is negative 1/2, and the x value here is positive 3. So for part A, we can say that the solution is x equals negative 1/2 or x equals 3. Now, just for clarity, you can actually solve this equation algebraically. So what I can do here is I can subtract 5x and subtract 6 from both sides, and that's going to give us 2x squared minus 5x minus 3 is equal to 0. From there, you can factor the quadratic here. And so if we factor, just take it on faith here. I'm just going to factor this. You can check my work. But you get those two factors. And then if you set each one of these factors equal to 0, you're going to get x equals 3. And here you get x equals negative 1/2. So we're not saying that solving equations graphically replaces solving algebraically. What we're saying is that we can use graphs to help us solve equations. Now for the second part, we want to know when is 2x squared plus 3 less than or equal to 5x plus 6. So that means we want 2x squared plus 3 to be below 5x plus 6, which means we want the parabola to be below the line. So you can see the line is here, and the parabola is here, and the parabola is below the line right in here. So the solution here is going to be all of the values of x between these two numbers. And again, this was negative 1/2, and this was positive 3. So the solution to part B is all values from x equals negative 1/2 up to positive 3. And notice that it's including, right? We have inclusion here because there's an equal sign there. And finally, for the third part, we want to know when is the parabola 2x squared plus 3 above the line 5x plus 6. And you can see the parabola is above the line out here. So that's this part of the graph. And also the parabola is above the line out here. It's this part of the graph. And so the solution for part C is going to be all values of x from negative infinity up to negative 1/2 union all the values from 3 to infinity. And actually I made a mistake here because notice that there is no equal sign on this. And so we are not going to include these endpoints. Let's change those into parentheses. There we go. So there is the solution for part C. So in the next example, it's very similar. We want to solve the given equation graphically, but there's another way you can do this. So for part A here, we have x cubed plus 6 is equal to 2x squared plus 5x. Rather than graphing these functions independently, what if I just set everything equal to 0? So I'll subtract 2x squared from both sides, and I'll subtract 5x from both sides, and that's going to give us x cubed minus 2x squared minus 5x plus 6 is equal to 0. So to solve this, I'm going to think of a function f of x as the function that you see here. And I'm going to graph that function. And so here is the graph of that function. Now, what we want to do is we want to find out when is this function equal to 0. Well, if I set this function equal to 0, I'm simply looking for the x-intercepts. And you can see on this graph, we have an x-intercept here. That's at x equals negative 2. We have one here at positive 1, and we have one here at positive 3. So the solution for part A is x equals negative 2, 1, and 3. Now for the second part, we're trying to solve when x cubed plus 6 is greater than 2x squared plus 5x. But again, if I subtract 2x squared and subtract 5x from both sides, we can think of this inequality as the same as this inequality. And if I let f of x be this function, which means it's equal to this over here in terms of its graph, then when f of x is greater than or equal to 0, simply means when is it above the x-axis, right? When it's equal to 0 is when it touches the x-axis. So when it's greater than or equal to 0 is when it is above or touching the x-axis. And you can see that the graph is above the x-axis here. And also it's above the x-axis here. And so for what values of x is that true? Well, it's for all the values of x in between -2 and +1. Also, all of the values from +3 to infinity. And this time it's inclusive because we do have an equal sign here. We can also use the graph to help us understand what it means to be increasing or decreasing. So we say a function is increasing on an interval if f of x1 is less than f of x2 anytime x1 is less than x2. Now that can be a little bit confusing, but if you think of a graph, a function is increasing if it is going up. So when you read it from left to right, the graph is going up. Now mathematically, the way we describe that is we say if x1 is less than x2, then f of x1 is less than f of x2. In other words, it's getting higher. Decreasing has the opposite meaning. So decreasing means the graph is going down. And that would mean that anytime x1 is less than x2, f of x1 is going to be greater than f of x2. That's what it means for it to be going down. So for example, here the graph gives us the weight of a person at a particular age x. Determine the intervals on which the function w is increasing and also on which it is decreasing. So we can see for this person at birth, they are here, and then their weight is increasing all the way up until they reach this age. And then the weight is the same from this age to this age, and then it increases again, and then the weight decreases, and then it stays the same. So when is it increasing? So W is increasing on what intervals? Well, again, it's increasing for this part right here. So if we interpret that, it appears to be somewhere around age 24 or so. So we're going to say it's increasing on the interval from 0 to 24. Union, it is also increasing from this age up to this age. And that appears to be from the age of 35 to the age of 40. Now, again, there's no real exact answer here because when you're looking at a graph, one of the downsides is that sometimes you have to approximate values. So you have to go by what it appears to be. Now, when is it decreasing? Well, we talked about that it's decreasing for this part right here, right? This is the only part for which it is decreasing, and that happens from age 40 up to age 50. Once again, find the intervals on which the function increases or decreases. First of all, we have the function f of x here. We want to sketch the graph. I've already done that for you. So here is the graph of that function. Find the domain and range of this function. So for part B, the domain is clearly all real numbers, which we can say is -infinity to infinity. That's because there is nothing that's restricted. The range for this graph is going to be all the y values that are covered. Now, if you look at this graph, the highest y value is right there. And that appears to be y equals 32. And that's because each of these marks represents 2 units, right? So the highest y value is 32. And it covers every y value below that all the way down to -infinity. So the range is going to be -infinity up to 32. Now for part C, find the intervals on which f is increasing and also on which it is decreasing. So f is increasing when it is going up, and we can see that f is increasing all the way up to here, and then it decreases, doesn't it? So it decreases here, and then f increases again here, and then it decreases for the rest of the time. So it is increasing on all values of x less than or equal to -1, or actually we'll just say less than -1. So minus infinity up to -1. Union, it's also increasing from x equals 0 all the way over to x equals 2. And it is decreasing everywhere else. So it is decreasing from x equals -1 to x equals 0. And also it is decreasing when x is bigger than 2. So we'll just say 2 to infinity. Next, let's sketch the graph of the function f of x equals x to the 2/3 power. This is a kind of interesting function, has a different shaped graph than what we're used to. So x to the 2/3 looks like this. Now let's find the domain and range. So once again, the domain is all real numbers. You can kind of see this on the graph. There is no value of x that is not covered. But the range is certainly not all real numbers because you can clearly see that there are no negative y values. So the lowest y value is 0 and the highest y value is infinity, right? Because this graph keeps going up and up forever. And then again, find the intervals on which f is increasing and also on which it is decreasing. So f increasing on what interval? Well, it's increasing here, right? And so that would be from 0 to infinity. And f is decreasing here, right? Because decreasing means going down. And so that's going to be on the interval from -infinity to 0. We can also use graphs to help us find extreme values of a function. And these are what we call local maxima and minima. Now, maxima is just sort of a plural for maximum, and minima is a plural for minimum. So what does it mean to be a local maximum value? Well, a local maximum value is a value on the graph that is higher than all the points right around it. Okay, so if you look at this graph over here, we have a local maximum here, right? This is higher than all the points right around it, but it's not an absolute maximum, right? There are other points on the graph over here that are higher than this point. So we can say that this point right here is a local maximum. Now, likewise, this point here is also a local maximum, but this point actually is the absolute maximum as well because it is the highest point on this graph. Local minimums basically has the same meaning. It's just that the point is lower than all the points right around it. Okay, and that's what these definitions say. So when you read this definition, it says f of a is a local maximum of f if f of a is greater than or equal to f of x when x is near a. So that's what we mean when we say that it's higher than all the points right around it. And then for local minimum, all we do is we switch that inequality from greater than to less than, and it's the same meaning. So for this particular problem, find the local maximum and minimum values of the function f of x equals x cubed minus 8x plus 1, and we're going to round that to 3 decimal places. Okay, so I've taken the liberty to graph this function. This function is not easy to graph, so I did it on a graphing calculator. And we can see that we have a local maximum right here. Okay, so I'm going to say max, and we have a local minimum right here. But if you zoom in a little bit, you can see that it's not really easy to see exactly what this value is. So what I'm going to do here is use the graphing calculator to give me a little more information about those 2 points. So now here is the same graph, but now I have information about those 2 points. So what are the local maximum and minimum values of this graph? Well, now I can say the local max is 9.709, and that occurs at x equals negative 1.633, right? That's where that is occurring. And then the local minimum is negative 7.709, right? That's this down here. And that occurs at the point x equals 1.633. So we can use graphing calculators to give us more detailed information. Now you might be wondering, how would we get this information if we didn't have a graphing calculator? Well, this is actually what we learn in calculus. And that concludes this video lesson.